Solve for x. In part A, we're asked to solve log of x is equal to 3 for x. Well, if we understand common logarithms, then this is fairly easy. A common logarithm is simply a power of 10. So in this case, x must be the third power of 10. 10 to the third power is 10 times 10 times 10, which is equal to 1,000. Now, a more formal way to solve this equation is to think of undoing. We have the logarithm of x is equal to 3. How do we undo taking a logarithm? Well, the inverse of taking a logarithm base 10 is to exponentiate base 10. So the first step would be to exponentiate both sides base 10. Now that we've exponentiated both sides base 10, we use the inverse property. Exponentiating base 10 undoes taking the logarithm base 10, and that just leaves us with x. So in this case, the exponentiation base 10 and the common logarithm cancel each other out, and we're left with the argument of the logarithm, which is x. So we get x is equal to 10 cubed. But 10 cubed is 10 times 10 times 10, which is 1,000. So x is equal to 1,000. And for part B, we're asked to solve the equation log of x plus 1 is equal to 3. Again, remembering that a common logarithm is a power of 10, this means that x plus 1 is equal to 10 to the third power. So x plus 1 must be equal to 1,000. But if we want to solve it more formally, again, to undo the logarithm, we'll exponentiate both sides base 10. On the left side of the equation, the exponentiation base 10 undoes taking the logarithm base 10, and that leaves us with the argument of the logarithm, which is x plus 1. And on the right hand side of the equation, 10 cubed is equal to 1,000. Now we simply take away 1 from both sides of the equation, and that leaves us with x is equal to 999. And we can clearly see that if we substitute 999 for x, we get 999 plus 1 is 1,000, and the logarithm of 1,000 is equal to 3. That checks out. For part C, we're asked to solve the equation 3 times the logarithm of x is equal to 5. Our strategy is going to be to isolate the logarithm, and then we'll exponentiate both sides base 10. So first of all, divide both sides by 3, and that gives us the logarithm of x is equal to 5/3. Now exponentiate both sides base 10. Using the inverse property, the left side simplifies to x, and the right hand side will just leave that as 10 to the 5/3 power. And to check our answer on a calculator, we could enter 10 to the 5/3 power. And be careful to put the 5/3 power in parentheses. Store that answer as x. And we can see that the value of x is approximately 46.4. And then we go back to our original equation, and on the left hand side we have the expression 3 times the logarithm of x. So we enter 3 times the logarithm of x, and we verify that that is equal to 5. It is, and so we're confident that our answer is correct. For D, we're asked to solve the equation the logarithm of x plus 1 minus the logarithm of x is equal to 1. This equation is a little bit different in that it has 2 logarithms rather than just 1. So our strategy will be to use the properties of logarithms to create a single logarithm, and then we'll proceed like we did in parts A through C. So in part D, we've got a difference of 2 logarithms, so we can write that as the single logarithm of a quotient, the logarithm of x plus 1 divided by x. Now that we have a single logarithm on the left-hand side, we'll exponentiate both sides base 10. On the left-hand side, we use the inverse property to simplify the expression, and that leaves us with the argument of the logarithm, which was x plus 1 over x. And on the right-hand side of the equation, we evaluate 10 to the first power, which is just the number 10. In order to solve this rational equation, we can multiply both sides by x, and that gives us x plus 1 is equal to 10x. Next, take away x from both sides, and we get 1 is equal to 9x. And finally, divide both sides by 9, and we get x is equal to 1/9. Let's check our answer. 1 divided by 9, we store that as x. It's approximately 0.11. And then we enter the left side of the equation, which is the logarithm of x plus 1 minus the logarithm of x. We press enter, we get the number 1, which is the same value that we have on the right side of the equation, and so we've solved the equation correctly. For E, the equation looks very similar to the equation for D. We have the logarithm of x minus the logarithm of x plus 1 is equal to 1. So the first thing that we'll do is to use properties of logarithms to create a single logarithm. This time we'll have the logarithm of x over x plus 1 is equal to 1. Next, we'll exponentiate both sides base 10. Using the inverse property, the left side simplifies to x over x plus 1. And the right side of the equation evaluates to 10. So this time we multiply both sides of the equation by x plus 1, and on the right side of the equation we'll be left with 10x plus 10. Subtract 10x from both sides, we get minus 9x is equal to 10. And then divide both sides by negative 9, and we get x is equal to minus 10/9. So let's check. Minus 10 divided by 9, store x. And then go back to the original equation and enter the left side, the logarithm of x minus the logarithm of x plus 1 and this time we get an error message, a non-real answer. Let's go to where the error occurs. Okay, we can see that there's an error in the first expression. Let's see why. X is a negative number and we need to evaluate the logarithm of that number. Well, the domain of a common logarithm is all positive numbers. You cannot find the logarithm of a negative number when you're working with real numbers. So the logarithm of a negative number is not a real number, and therefore this solution does not work. So this equation does not have any real solutions. So no real solution.